Hi everyone, Jeremy here, and welcome back to the Towards Data Science podcast. On today's episode, we'll be talking about what's known as the AI scaling hypothesis. Now, this is the idea that as AI techniques like deep learning are scaled up using more compute resources, larger models, and more data, their performance improves in ways that we can actually predict ahead of time. Now, the scaling hypothesis is really important for independent AI researchers who can't always afford to build huge AIs. If they can build a small, cheap system and extrapolate its capabilities using scaling models, then they can punch well above their weight without needing an affiliation with companies like Microsoft or Google that normally sponsor this kind of research. Now, my guest today is Andy Jones, an independent AI safety researcher who's been investigating some surprising and fascinating aspects of the scaling hypothesis that have important implications for the future not only of AI in general, but AI safety research in particular. So we'll discuss his work as well as what it means for the big picture problems in AI safety and his motivations for working on those problems as well. I had a ton of fun with this one, and I hope you enjoy the episode as much as I did. All right, well, Andy, thanks so much for joining me for the podcast.
And thanks for inviting me along.
Your Twitter bio describes you as an indie AI safety researcher, which I think is a really cool thing that people who aren't in the AI safety space might not really kind of understand or recognize as an archetype. So I'd love to ask what brought you to independent AI safety research in the first place, and also what does your day-to-day look like in that context?
I will first disclaim that I can't claim to be an archetype of any sort or a prototype of any sort. I do describe myself as an independent AI safety researcher, and I think over the course of the conversation we're about to have, it'll become more clear what that means. On the day-to-day, what it means is much the same day-to-day that many of your listeners will have. I used to work as a quant trader, as a data scientist of a sort for a hedge fund, and my work since then independently has been largely the same. I type. I'm a very specialized typist if it comes down to it. I read research papers, I go for walks and think about the things that I'm trying to solve. And then I come home, put them into code and discover it's all broken and does it work? And we rinse and repeat over and over again, and gradually progress is made. Hopefully that's something that's a familiar loop.
Yeah, I'm sure it will be to a lot of people. And I'm curious, what brought you to this area? Because there are a lot of people who work at the intersection of, let's say, AI and what I might call social good or generally the good of humanity. And they go about it in different ways. Some people do research into AI ethics. Some people do research into, how to deploy AI for use in third world countries, stuff like that. I'm curious about, so why AI safety and I guess AI alignment, that sort of ecosystem?
Well, there are many ways to answer this question, depending on how deep into the past we want to go. I think there are two cruxes that are worth mentioning. The first is about 5 years ago, I was working for a hedge fund and making very good money. Let's not beat around the bush here. But I don't really have many expensive things I care for. I don't particularly want to live in a large house or go on holiday. And so I was mostly working to retire very early. When into my work group at the fund I was at came a friend, Adam Gleave, who is now a researcher at Berkeley, also working on AI safety stuff. And he introduced me to this effective altruism stuff and this idea that if you have made it to the top of Maslow's pyramid, maybe you should start thinking about other things you can do in the world in terms of making it better. And this is stuff like donating to anti-malarials in the third world and deworming and so on and so forth. So this was the first key turning point that got me more interested in the things beyond what was immediately interesting that day and just retiring early for want of a better justification. And over the next couple of years, this came to be a larger and larger part of my life. The best model I have for myself is that I'm the average of whoever I've been hanging out with these past couple of years. Mm-hmm. And after being introduced to effective altruism, there is a very large and active group in London. And these people have come to be like most of my friends. And you can't help but turn into your friends given time enough.
Yeah.
And one of the things that tends to happen when people spend a lot of time thinking about how to make the world better is either they will go quite hard on global health, so to speak. This is anti-malarials alike, or they will come to believe that animals have some amount of ethical utility as humans do, and you end up going down the path of, well, you can save many more animal lives for a certain amount of money than you can humans, and this is a better effective use of my time and effort. Or you start to think about future humans, this idea that it is easier to save or preserve a life in the distant future than it is today, flapping the wings of the butterfly, so to speak. And this is nowhere near as concrete as the core global health stuff. I should put up front that I think there are very many good arguments about this, over this, and I think there is a cynical take that a bunch of computer scientists went out looking for a way to improve the world and found a computer science problem to solve. And certainly this kept me cynical about the entire AI risk, X risk, as it's called, extinction risk work for a very long time, to the point that I am now on a regular basis groveling in apology to various friends who I mocked about this for many years. It now turns out that they were right, I was wrong, and I just have to live with that.
I think that's a good place to start with this too. Everybody has their own take on, well, either how likely they think extinction due to something like AI is, and also what the arguments are they found really compelling that brought them to that position. I'd love to hear what that is in your case.
I think the main place in which I disagree about the way to go about helping, or to go about thinking about the future, which I think is the core of this, is whether you think there is a fairly narrow path that the future might take and you have a strong belief in that path, or whether you think there are many different ways the future can go and you're entirely uncertain about which way it could go. So if you were the kind of person that just believed, or if you were like the single path person, the forecasting literature calls this foxes versus hedgehogs, for want of just two nouns that will fit to a phrase. The fox knows one big thing, the hedgehog many little things. And there's a trade-off between, this feeds into how you think about the future. But I cannot claim to be confident about any particular path that the future is going to take, especially around AI. But I think there are certain paths with some small likelihood that will both have some tremendous impact on the way things will come to be, and which I can have a decisive influence upon in this place and in this time. I think the usual analogy I bring up here is, I think there is like an 80% chance maybe that I'm a nuclear physicist in 1890, and it's still 50 years or so before anything interesting happens, and I'll be old and gray before anything interesting happens. And there's a 10-15% chance that I'm a nuclear physicist in like 1939, and really, it's time to get your nose down to the grindstone and think about what's going to happen here.
And in other words, specifically with respect to AI, that we might be, you think there's like 10 to 20% chance we might be on the cusp of something like general human level AI, something like that?
The idea of human level intelligence is fairly charged. And 100 years of sci-fi will do this. So the phrase that people are generally more comfortable with, I'm more comfortable with when we discuss this, is simply transformative AI. AI that will change things as we know it. Something equivalent to the invention of electricity, though some gads on Twitter will call it equivalent to the invention of fire. I think it's a bit strong, that, but I understand where they're coming from. And yeah, I think there is some small chance. It's putting exact figures on this is a fool's game, because someone will come back in the future and point to it and said, you said a thing, and it turned out you're wrong. And yes, that's unlikely. But the point is that there is some, I'm influenced largely by the small chances of things. That another analogy is if you're thinking about whether to play Russian roulette, it's not the 5 empty chambers you spend your time thinking about. It's the one that's full, despite it being the unlikely case.
Well, and there is an amusing sort of impotence of even experts when it comes to, that's notorious in science when it comes to predicting the future. I mean, I think if I'm remembering the names and dates correctly, it was late 30s, Leo Szilard or something, had given up essentially on the idea of the chain reaction. And then I think the day that he wrote his letter officially giving up on this, there was a big breakthrough in Germany or some German lab where anyway, the bottom line is these things are inherently unpredictable, right? I mean,
I do not like that that's the case, but yes, it does seem to be the case. And in fact, I will make that anecdote when I try to explain this stuff in future. That's an excellent example. I will say that quite often there is some recall bias here in that we mentioned, say, Leo Szilard being wrong about nuclear energy, whatever the anecdote was about, shortly before it was in fact possible. But there are many more people in history who have said a thing, turned out to be wrong, and then stayed wrong.
and about 100 of them are called Nostradamus. So. Yeah.
Yes. Well, there's the two ends of your scale. Leo Szilard lived in 1939 and Nostradamus. Yeah, there you go.
Okay, good. So I'll have to use that in the future on a scale from, yeah, great. Well, yeah, so I think that provides some good context then in terms of what brings you to this. So there's a sense in which, the argument can be made that we ought to worry a lot about low probability, very high impact outcomes. So when it comes to AI, what are the specific outcomes that you are most concerned about changing or addressing? Obviously, specifics are going to be hard to come by here because none of us can predict the future. But just qualitatively, if you can sketch out maybe.
I think it runs the gamut in terms of, I think the two axes to discuss these things over is first time horizon into the future. So we could talk about the short scale impacts of transformative AI, such as mass unemployment, and then scale out to much further distant things. So, or hopefully much further distant things about who ends up inheriting the galaxy kind of stuff, like real sci-fi stuff. I think the thing that is easier to talk about without sounding too much like a crank is the short-term impacts of things. And I think the other axis to consider things along is, it's not so much an axis as a choice of reference class. I think when you talk about the way that AI progresses, you're largely influenced by what you think AI is going to be like, whether it will turn out to be like humans, whether it will turn out to be another mundane technology like fire, electricity, microchips, the internet, or whether it will turn out to be like the machine learning we have already. And I think these three sets of choices of reference classes give very different, they describe broad chunks of how you think the future may go. So if, for example, you think AI is going to turn out to be like human intelligence, like if the idea is that if you go about building an intelligence by whatever mean you choose, you come out with something that looks like a human intelligence and acts like a human intelligence, then you may have ideas along the lines of, say, Robin Hanson's circa mid-1990s. So Robin Hanson is an economist who is one of those frustrating people who was right a long time before I was. And I have a list of these people. Don't worry, I'm keeping track. We're going to mention a lot of names today. And one of Robin Hanson's key ideas was the idea that if you can have a human-esque consciousness running in simulation, and you ask this human to design a microchip to run its own simulation, then you have some kind of feedback loop. And this is one of the original conceptions of the singularity in the more serious literature. So you have the simulated scientist who designs a better microchip to run his own consciousness on, and you repeat the loop and it gets faster and faster and faster and faster. And in that case, the singularity, I'm not a huge fan of the concept because I think it excuses people for reasoning through it.
Right.
I think it's a get out clause quite often, or it can be the start of an interesting conversation, but I don't think it should be the end of one.
I really agree with that. I think that's something I've never kind of given myself permission to think aloud, so to speak. But it very much seems that way. I mean, by analogy with, we always hear about physics and quantum mechanics. A black hole is a singularity. It's a place where all known laws break down, and implicit in that is the idea that we should stop thinking about what happens at that stage. Sort of seems similar here. Now the Robin Hanson simulation singularity, where you talk about, the simulator simulates a simulation, which simulates simulation, and so on. I guess that's one axis. There's an AI version of this as well, or do you consider those two distinct things?
Sorry, can you rephrase that so I get the sense of what exactly you're asking?
So Robin Hanson has this idea, as you mentioned, that you have a simulator who generates a simulation, that allows him to live at a faster rate, so like an accelerated life, basically, have more life experience. And in that simulation, he can create a new simulation that accelerates it further. So you essentially have this infinitely increasing rate of life experience collection, with probably a bunch of physical bounds. Like you'd actually probably run up to a bunch of issues there in the limit. But when we talk about AI, it seems like there's a different kind of singularity that's discussed in that context. But I'm curious if you think that those two might actually be equivalent in some way, or do you really see them as different things?
So the reason that I was caught by your question is when you said, do you think there's an AI version of this? In my head, there's no distinction between the version of this with human brains running and the version with AI brains running. I have drunk the Kool-Aid here. I think of AIs in a very similar way to, I think, I use it, yeah, it's hard for me to distinguish the two, but certainly the equivalent, or maybe the most plausible equivalent as of like this year might be you build a language model, for example, which is the shiny new thing, and you get to the point where it can write better code for writing language models than humans can itself. And this is in a sense, there's not as much agency in there. It's not as good of a sci-fi story in a sense, but it seems remarkably more plausible sitting here in 2021.
Good. Okay. For what it's worth, that's where I thought you were going. I just wanted to make it really explicit that the mapping was there. Yeah. So, because I think there are a lot of people who do struggle with that kind of distinction, and we're not used to thinking of like AI systems as general reasoning systems, things that can make their own AIs. I mean, in the limit, there's no reason why an AI system couldn't, if a human can build an AI and improve AIs, there's no reason AIs couldn't eventually do that better than us. And if that's the case, sort of like the same accelerationist thesis applies, right?
I entirely agree. We will talk later about the various like anxieties I had around the emergence of GPT-3. One of the core issues there is I went from thinking that the first jobs that would be automated by AI might be factory workers to thinking that the first things that were automated by AI might be AI scientists. And speaking as an AI scientist myself, that made me much more nervous. It's one thing to insult the Luddites when you think you're a mill owner. When it turns out you're the weaver, you have a totally different opinion.
I think that's a very fair point and a good sort of introspective analysis. Now, maybe this gets us down the path towards talking about scaling a little bit. People talk a lot about, making big AI systems, larger AI systems, scaled AI systems. I'm sure a lot of listeners have heard these terms like in the news, and you probably have a vague sense of what these things mean. But I'd love to hear it from you as somebody who's done research on scaling. What is meant by scaling? Like, what is the size of an AI system? How can we measure that? And what are the measures that matter?
It's not even a good analogy, but the analogy that we have to work with when we start to talk about the size of intelligence in a sense is we have to talk about humans and animals. And everyone is familiar that there are many animals on the planet with many differently sized brains. And it's not a direct link between the size of the brain and the intelligence of the animal. For example, quite famously, whales have brains substantially much bigger than human brains and do not seem to be anywhere near as smart, though Douglas Adams may disagree. But there is some factor that we describe that we usually call the encephalization quotient, which is the size of the brain divided by the size of the body mass, because it turns out you need a lot of brain just to run a lot of nerves and a lot of the muscles. And if you take this then and you plot out your rough impression of how smart an animal is against this thing called the encephalization quotient, then you get a fairly direct trend that animals with bigger brain to body ratios do seem to be smarter. So in a sense, bigger brain to body, more intelligence. And it is a long running discussion in the people that study this kind of thing about how seriously to take this kind of encephalization quotient, whether the key property of humans being as smart as they are is in fact the size of their brains relative to their body, or whether there are other more subtle structures in there that actually dictate the emergence of things like language. Now, in AI over the past 60, 70 years, how long has it been since we first started mucking around with neural networks? Back in the 60s or so? As silicon has gotten cheaper, as compute, so to speak, has gotten cheaper, as memory has gotten cheaper, we've been able to build bigger and bigger and bigger models. And around about 2010-ish, we finally figured out that a lot of old simple techniques, deployed on modern fast hardware, deployed on GPUs, NVIDIA's GPUs were the key to this whole thing, deployed on parallel structures, fast parallel compute hardware, could lead to surprisingly intelligent output. You went from, quite famously, there was an XKCD comic, famously among the people that are likely to be listening to this, not famously in the wider world, bemoaning how hard it was to distinguish a bird from, I can't remember what the contrasting thing was, but trying to recognize a bird in an image or something. And this was shortly before the emergence of neural net image recognizers. And now it's something that a 14-year-old can knock together, 6 hours on a Friday night. We have moved the goalposts quite substantially in that we no longer think of this as intelligent behavior, but it is, looking back, quite astonishing. As someone who, got to grips with machine learning in the early 2010s, I thought this was a hard thing once, and now it's a very simple thing. And we can come back later to this moving the goalposts effect and how once upon a time, humans proclaimed things like chess to be the ultimate of human intellect.
Yeah.
And people aren't so keen on doing that anymore. Humans don't end up looking good if you choose chess as your objective. But this progression in the size of the speed of the hardware we use, and implicitly the size of the models and the compute intensity of the models we train on this hardware, with the capabilities of this hardware, is in retrospect quite striking. And about 2 years ago, 3 years ago, 4 years ago now. So the famous paper in this area was by OpenAI, but there was actually a small amount of preceding work, first from a Baidu researcher in about 2017. And then there was a bit out of MIT by a guy whose name I cannot remember right this second, looking at similar things in about the same time that OpenAI were talking about it. But the idea is that if you take a very specific kind of AI, you don't talk about AI in general, brains in general, you take a very specific one, and you increase the amount of hardware available to it, increase the amount of RAM memory available to it, the amount of time you're willing to train it, the amount of GPUs that you use to train it, then the quality of its predictions, of its abilities, increases in a fairly predictable manner. And it does this over many orders of magnitude. I'm going to pick some numbers out of a hat here. These are certainly not the ones in the paper, but the ones that OpenAI looked at, and I'll choose this because it is the best known work, it's certainly the most famous work. They took a thing called a language model. And we discussed language models briefly earlier. But the idea with a language model is that you take the entire of the internet, or a large fraction of it, and you give the internet a sentence from this giant corpus, just one chosen at random, and you ask it to predict the next word. And this is a startlingly simple thing to try to do. Just keep on trying to predict the next word.
Like autocomplete.
Autocomplete, Mad Libs, yeah. Like something very simple like this. Or even just try to annoy your brother by trying to speak ahead of them and guess what they're going to say next. But this very, very simple task, it turns out, if the model wants to do it well, then it needs to acquire fairly substantial understanding about the world, the way the world works. In that, if the model sees the word red, then it needs to know that fire trucks are an object that are quite frequently red, in order to be able to say that fire truck is a likely next word. And so by training these things on billions of words with lots of hardware, quite subtle patterns seem to get embedded into the model. And the most impressive example of this is there is a guy called Gwern, semi-famous on certain parts of Twitter, and he keeps a collection of the various things that these very highly trained language models have produced. And the most impressive ones to me were that when you have, say, 10, 20 billion parameters in your language model, you can write a thing such as, and here is a Harry Potter parody in the style of, and the name of every famous author in history has gone out of my head right now, in the style of Shakespeare, so to speak.
Yeah.
And the model will take these things and say, what is the most likely word to happen next? And come out with a very impressive parody of Harry Potter in the style of Shakespeare. It has picked up the idea of how Shakespeare speaks. It's picked up the idea of what characters are involved in Harry Potter and there's a wizarding school and what it's like. And all this from just trying to do better at predicting the next word.
Do better is a complicated term, obviously, in this context, but it seems as if there are a couple of different axes that we need to pay attention to separately. So as we scale these models, as we give them more RAM, more compute, more data as well, all at the same time, even if the model is relatively simple, we scale these simple things, and then not only do they become better at carrying out the specific task that we assign to them, in this case, something like autocomplete, but when you talk about, write this Harry Potter story in the style of Shakespeare, that's a task that I think most people would not normally associate with something like autocomplete. And it kind of hints at a level of, let's say, cross-task capability, dare I say generality, that perhaps might have been surprising. Is that an accurate analysis, or would you disagree with that?
I would describe it as accurate insofar as I was very surprised at the time. And certainly as with many things, once you know it's there, you look back and find it in many other places. In that, again, I've drunk the Kool-Aid here, and I do not consider that what you're describing here is generally called meta-learning, the capability to learn on one task and coincidentally be able to specialize in another task down the line, or do better in other tasks down the line. And at the time, I was very surprised. In hindsight, it seems surprising not to think this would happen, that if you ask a model to predict words in sequence and you give it enough hardware and compute to be able to do this very, very, very well, then in order to get this tiny improvement in being able to get the next word, it needs to acquire like fairly complex models about how things are. And then this carries over to other places. All this structure is just carried around with it, gets it for free. I think, again, I'm reaching for analogies here, but if you look at a baby who's just playing with their blocks, observing the world, playing with the blocks, and just garbling along, one way to think about it is that they may be developing internally some very sophisticated models about the way the world works, the way that Euclidean geometry works, the way that gravity works, despite not having any real theory for how these things work, any understanding of how these things work. And yet they can interact with blocks, they could juggle them a few years later just fine. So yeah, they've trained on this this is all called self-supervised learning in contrast to supervised learning. In supervised learning, you usually have some kind of label telling you what is a good example and what is a bad example. Whereas in self-supervised learning, you are just trying to predict some other bit of structure in the data. And the wonderful thing about self-supervised learning is it just comes for free for living in the world.
So this is interesting because one of the big take-homes appears to be that although GPT-3, and there are all kinds of crazy examples, as you say, Gwern and others have highlighted some really amazing things GPT-3 can do that, we've talked about, let's say, translating between literary styles here between J.K. Rowling and Shakespeare, but of course there's also translating between languages and some basic coding, like converting written work into code and basic web design work, stuff like that, that does appear shocking if you don't first think of all machine learning as an instance of meta learning. There's like some meta learning behind most stuff, some principles that generalize. I'm curious where you now see, looking back, where you might now see some hints of this in maybe earlier experiments that precede GPT-3.
The easy place, the cheap place, the lazy place to look for these kind of things is in earlier language models, in that going back to the days of Markov chains even. So a Markov chain is an extremely simple pre-neural network style of machine learning, where you just build a table of, if you see these 4 words, then what is the most likely one next? And this is so simple, most people, almost no one is willing to qualify it as intelligence. But still, these things will produce interesting Mad Libs, interesting, I won't even qualify, I can hardly even call it like poetry or whatever, it's too basic for this really. But certainly new and novel structures different from the ones that were in their training set. And this is so boring really that it doesn't qualify the phrase meta-learning, and that's why we didn't call it meta-learning at the time. It's only in hindsight, seeing what it actually happens when it's scaled up, that we start giving it a different name to this. I have a personal prejudice here that I suspect that the reason we have come up with the phrase meta-learning is that for a very long time, we did machine learning on very narrow data sets. And so there wasn't really any place in which it could surprise us. We trained image recognition models and then gave it images to look at. Right. Whereas, if you go look at Chris Oler's work on microscope AI and his discovery that if you train very good image recognition models, that comes up with concepts of geography and the like internally. It's not quite the same thing as GPT-3, but it's the same kind of surprisingly complex structure discovered from surprisingly simple inputs.
So this actually gets to something that I've often wondered about, language models. So it seems like language prediction or autocomplete, whatever this task is that we're describing that GPT-3 does, lends itself very directly to generality because language encodes all of our knowledge of the world. It's like the most direct way humans have. It's also optimized for communication, so it's easy to recognize when it's being used. But would you say now, given the Chris Oler image examples, would you say that it's the case that perhaps most tasks, when performed at outrageously high scales, outrageously well, eventually force the system that's performing them to develop a kind of generality, a kind of flexibility across tasks? Or is that overbroad as a statement?
Yes, it is overbroad, but yes, I agree with it. I am very much on board with the general idea that if you take some, let's call these broad tasks, things like recognizing objects and images or predicting words and language, or maybe in the future it will be predicting frames in videos or operating some fleet of drones, so to speak. That if these things have to interact with the world at large in some sense, possibly through some very narrow window of, say, language or text or whatever, then yes, they do seem to have to pick up very complex models in order to be able to do that task well. And it doesn't seem to be contingent on the particular kind of data you are feeding them. Having said that, my personal suspicion is that, yes, you are right, language is special in a way that other data modalities are, in that we collectively, as a civilization, as a species, have spent 10,000 years optimizing, well, I don't know how long language has been around for, but we've spent many thousands of years optimizing language to be a transport mechanism for describing the world around us. I would expect that language is a much more dense medium for encoding just the things we care about, in a way that images or frames of videos or general operation of robotic bodies might not be. So yes, this is one of those things that, again, is not surprising in hindsight, that language models would be the first thing to hit this like threshold of interesting generalization, just because the medium they work on is information dense in a sense that images just aren't. I should qualify a lot of the things I'm saying here. Sorry, I say I qualify, I think, in that I'm telling stories here which do seem to me to make sense. And by the way that you're nodding along, it makes sense to at least one other person in the universe. But this is not to say that there are not many other accomplished researchers, many who have been on this podcast, who deeply and vehemently disagree with everything I'm saying here.
Actually, that's a really good point, and I think it speaks to, earlier you were referring to the uncertainty bounds around these sort of, low probability and high impact events. And I think it's fair to say that the low probability part comes perhaps in large part, at least in significant part, from the objections of other people who know a lot more than certainly me. But so it's a complex space, but the thing is that ultimately there are no experts, as the nuclear sort of chain reaction example shows. Predicting this stuff is really hard, and in that universe, you kind of have to hedge your bets and make sure you're kind of being cautious. So I definitely appreciate that hedge. I think it's a responsible thing to do. That said, continuing under the assumption that we're both exactly
Absolutely,
right
yes.
about this naturally. So I think this brings us quite neatly to the moment that GPT-3 first comes out. I think it first came out actually as a paper, and somewhat silently. I mean, people recognized it as like, oh, wow, this is a cool advance. But it was only once you started seeing some of the beta testing, some of the use cases for me at least on Twitter, that I kind of went, oh my God, something big is happening here, and this could be really serious.
So yeah, I think I very much sympathize with that. There was the original, there was a paper called Scaling Laws in Neural Language Models, which came out early last year, early 2020. And I read this paper at the time and I dismissed it. It did not click for me whatsoever. I thought, okay, another interesting result coming through the archive today. Great, sure. And then 3 or 4 months later, this GPT-3 was announced in a narrow sense that they had a very nice blog post and a paper and gave beta testing access to a handful of people. And this is where you started to see various examples percolate through the internet. And again, I have to give Gwen credit here in that he collected a lot of very impressive examples. And it was his newsletter and his exclamations around it that convinced me that this was a big thing. Now, for background here, I've been keeping track of developments in AI for many years. I started in this space about 2012, 2013. And over that time, there have been quite a few instances of what I, in hindsight, called AI anxiety, that I have my idea of what AI should be able to do this year, and then it is blown through in some sense. And the earliest example of this was the Atari work out of DeepMind in the first half of last decade. I had a good few days where I was like, wow, this is a lot better than I thought it was going to be. But I very much managed to move the goalposts. I convinced myself that this was, not as impressive as it first seemed to be. And then the same with Go and StarCraft and with Dota. And then GPT-3 was just the kick in the teeth that was it was hard to move the goalposts as far as they needed to in this case. And that was what convinced me to sit down and think very, very hard about what place I would want to have in this brave new world. And there are 2 artifacts from my thinking in this time. There is one Reddit post in which I am fairly panicky, and there is one Less Wrong post in which I am fairly panicky. And in hindsight, I am somewhat embarrassed by the strength of my response there, but I think it's an honest response and it reflects the trajectory that brought me to where I am now. So these 2 posts were basically going, well, it's not going to stop here, guys, is it? It's not. If the problem is really that I keep on having to move goalposts, then we should put the goalposts on treadles here and just keep on moving them. How fast do they have to move to keep up with things? So if you accept that the goalposts are now going to move at a steady and increasing rate, the first thing to do is turn around and go, well, how fast are they going to move? What's the limiter here? What determines the progress in AI over the last 10, 15, 20 years? And the big enabler, there are other things, but the big enabler is the development and proliferation of cheap compute. Now, many of your listeners will likely be aware of Moore's law. This goes back to the 1970s and says that every 18 months, the density of transistors on a die will double. And this is a very narrow prediction. This is only useful within very specific parts of the semiconductor manufacturing industry, but it's being hijacked as a general description for the progress of compute as a whole. So I think I'm happy to talk about Moore's law in the sense of GPUs getting faster, despite the fact that the transistors are no longer getting smaller at that rate, and such like. But yeah, when you start to think, well, if compute doubles every 18-ish months, and there are a lot of predictions around this, if you're interested in this, go Google around for it, and you'll find much better predictions than the ones I'm giving you here. But if you assume that it progresses at some increasing rate, then what should you expect in the coming years? How much bigger will models be? How much faster will they grow? And the other factor is how much more money will go into them.
Right. So one of the big questions that you, and by the way, I should mention the as nervous as you mentioned you were, as you wrote up in particular this post on Less Wrong, I'm quite convinced that there was a minor ecosystem of people sort of nervously scratching their chins as they collectively read that post, I being one of them. I remember reading it and going like, wow, yeah, this is exactly the sort of panicked feeling I'm experiencing here. And to see it laid out, I mean, the case you were building, I think it'd be worth exploring that case specifically, sort of where you saw things going at that moment, and then exploring as well, like where your thinking has gone since then, because I understand that it's evolved a little bit too.
So so when I first started writing this post, which I'm sure will be linked at some point.
Yeah, we'll link to it in there.
Yeah. My main concern was the rate of compute increase. And that gives you one trajectory for how fast AI will get better. But really, AI has been a bit of a backwater of research these past 50 years. It's something that university professors do for funsies. It's what you do after you've got tenure. It's only been in the last few years that it started to look like an economically viable industry, that you could put money into training these very big models and then go sell their outputs to people and get more money back. And the moment something goes from being like a fun little research project to an economically viable industry, the amounts of cash involved change dramatically. Mm-hmm. So you have Nikola Tesla playing around on his mountaintop at one point, and then you have like a national grid 20, 30 years later. Like the moment serious corporations and governments get involved in this kind of thing, it goes from budgets on the order of like a few $100,000 per run. That was like a few years ago, and that was considered very expensive at the time, up to tens of millions, hundreds of millions, billions of dollars going forward. And this kind of dwarfs the progress in hardware. And this is the thing that really got me, that if some people in the right spots in the hierarchies of very wealthy corporations and governments decide that this is an important thing to pursue, things will change very, very rapidly. Now, what has qualified my panic since then is when I wrote the post, I was deliberately a coward in that I didn't put any concrete predictions in there, because I felt if I did this, I'd have egg on my face a year later. But looking back at it now, I wish I had, because it would be a good lesson having the egg on my face about the willingness to get panicked about things if you're not willing to make predictions at the same time. What
predictions would you have made?
I think at the time I was expecting a similar leap to GPT-3 in the next 12 to 18, 24 months. And we're about halfway through that period now, and it's been fairly quiet. And it could be that's because the big players are still revving up for some kind of big publication in the near future. Or it could be because it turns out that raising more than $10 million for a training run is a hard thing to do. The kind of people you need to convince are just not willing to give you that kind of money. Or it might be that there is some kind of hardware limitation, that if you want to bootstrap together 1,000 GPUs, that's one thing, but 10,000 GPUs is an entirely different kettle of fish. And coming up with the infrastructure to do this kind of thing is much harder than it might have been. So it was what I described at the time, I think, was an upper bound on progress, and then I over-focused on the upper bound. But this is me speaking from the other end of the hedonic treadmill, where I've adjusted to life in this brave new world, and I've now decided that it's totally okay.
Well, it does seem like the underlying argument, though, that the moment that machine learning switches from becoming this money sink to a money making machine, all of a sudden you kind of reach like a sort of economic escape velocity where people pour money in, they're able to build bigger systems, scale more, those systems can do more, and so on. So you sort of like start along what is, I guess, something like a roughly exponential trajectory, though I'm sure there are different arguments for the shape of it. But
Yeah, I broadly agree with this, but I will qualify the phrase again. The panicked way to look at it is that we are entering into the takeoff, and now this economic loop is closed, and more money will be fed into this system. The slightly more, or the more sanity-preserving version is that this trajectory has been running since the 1700s. That the moment someone built a machine that built a machine, that was all she wrote, and we've been living through the takeoff since then. And then it turns into the much more pedestrian problem of the fact that the world is moving faster than you want it to. And this is something that everyone throughout time, back to the ancient Greeks, complaining about how kids these days were writing things on tablets rather than memorizing them, has been complaining about. This is just an old people's problem. And that's what I cling on to here. That in fact, this is the reference class of AI as another technology rather than anything shiny and new.
This definitely seems to align with, so I have had a conversation with David Rudman, who works at Open Philanthropy, and he put together essentially a research project on the economics, or the history of economics, really, the history of human output over time. And he was describing how most economic, not most, I should be more careful than that, many economic models end up going to infinity in finite time. They end up predicting that the output of the human species will actually reach infinity in a finite amount of time. So this is not exponential, because exponentials, they go to infinity in infinite time. They just do it really fast. This is literally, you break the economic ceiling of the universe by 20 whatever or 30 whatever.
Yeah, it's every sigmoid looks like an exponential when you're in the middle of it, and every exponential turns out to be a sigmoid because you run out of space eventually.
Right, that's it. And so yeah, I guess that's another deep question, is like how singular is the singularity, and what is that upper limit? But yeah, distinct from that, I mean, I guess one of the observations that he made was, this is admittedly a very crude simulation that he was running. I mean, it has to be. You're looking back 10,000 years. What are you going to do? But he found that most civilizations that he simulated, starting about circa 10,000 years ago, do end up in this terminal state where the value goes to infinity. Or it crashes to zero because you deplete all the resources and there's a disaster. But details. I guess the bottom line is it sort of speaks to your point that there's a sense in which you could say that the moment, I don't know if it's the moment language was invented and all of a sudden we closed a sort of ideation loop, or the moment the telephone was, but they're different.
Honestly,
points,
it was RNA that was the mistake.
Well, and that kind of has you zoom out even more and ask, is the universe really fundamentally this bundle of particles that are parameterized by locations and directions, and those parameters jumble together like an evolutionary algorithm that ultimately...
This is Jeremie, the quantum physicist, coming out, I can tell.
Yeah, I've lost the plot now. But anyway, the point is, there's a big picture, folks.
If we have lost the plot, then we lost the plot quite a long time ago in this.
Yeah, that's fair. To your point, though, it's like, when you get into the game of saying, like, no, now is the time that we hit escape velocity, it sort of becomes a bit of an unsolvable problem in that sense.
So we've talked about my anxiety, my AI anxiety about this, and then it might be worth moving on to the ways I've tried to cope about this. You said that there's a cottage community of people panicking about this stuff. And to be clear, I'm no way the first person to get to this. As I say, Robin Hanson was getting wound up about this in the 1990s. And Eliza Yudowski and the Less Wrong folk have made like a living out of panicking about this stuff for the last 20 years. And again, another group of people who were very right and I was very wrong. And I'll hopefully get to apologize to them about that someday. But for me, the arc of the past 12 months has been, I have discovered over the course of my life that the best way to deal with my anxieties is to work on my anxieties, to normalize them and bring them into the set of things that I can make progress on. And AI has turned out to be one more thing like that. That while this might be, the future of the universe, if we're going to be really hyperbolic about things, there is some small part of it that I can focus on and say, this is mine and I can make progress here. And so in the months after my Panicked Less Wrong post, I did a lot of reading on what other people had thought so far about what's called AI safety or AI risk. So AI risk is the broadest area. AI safety is a slightly narrower area about, okay, what do we do about this AI risk? And then AI alignment is possibly an even narrower set of, okay, and how can we get AIs to do what the thing we want as a way to play towards safety and reducing AI risk? And there's a fair chunk of material written about this by people who have thought very long and hard about it and who are much smarter than I am. And my goal in reading all of this was to try and find a space in which I thought I might have a comparative advantage. So the effective altruists that I have hung out with the last few years have this tendency to analyze problems to work on in terms of importance, neglectedness, and tractability. So the kind of thing that you want to look at if you're looking for a way to improve the world is something that's important to work on, something that's neglected in the sense that no one else is working on it yet. So something like climate change, extremely important problem, but it has a lot of very, very good people working on it, people who are far smarter and better resourced than me. It's not likely that I can make a serious contribution there. And tractable in the sense that if your problem is like, if you've chosen original sin as your problem that is like important and neglected, it's not tractable, mate, step off, find something else. But in my reading up, I made a list of what I call my bad idea list. One of my favorite ways to come up with research ideas is to accumulate over the course of a few months a lot of very bad ideas and hope that against this backdrop of very bad ideas, something emerges which looks like slightly less bad than all the others. And the one that I settled on was this idea, this paper this turned into the paper I eventually wrote, of that if my problem is if my source of my anxiety is very large AIs, but me with like my fairly cheap standard of living can only afford very, very small AIs, then what can I use the small AIs to say about the big AIs? And this leads into the area of scaling laws, because this is exactly what scaling laws do. They say, well, we've taken a very small AI and it performs like this. Or we've taken a slightly larger one and it performs like this. And if we continue on like this, maybe we could say something about AIs far bigger than the ones we could train. This would be like the analogy would be if you see an insect behave in one way and you see a rat behave in another and a monkey behave in another, maybe you could say something like humans. And I think that analogy is accurate in how inaccurate your predictions are likely to be about any specific trait. But the general complexity of the behavior, the trends of the things would hopefully be apparent. Though I'm very much like, this is what's called ex post reasoning. I'm coming up with an explanation after having observed the evidence. It's cheap, it's easy.
Oh, it's the funnest kind of reasoning, though.
Absolutely. Love it. Make a career out of it. But having identified scaling laws as like a viable way to connect the small to the large, I then started, because I am, even compared to the people who are studying scaling laws, I am very resource bound. And so the thing I caught on to was whether, as well as scaling the size of the agent, of the size of the AI, maybe I could scale the size of the problem it was interacting with like a vain hope that maybe a small AI solving a simple problem tells you something about big AIs solving complex problems. Like this would, in a sense, we know this to be true. This is what we've done all along in all of research ever. We've taken very simple, like crayon style models of the universe, solved something there, and then used that to say something much more interesting about the world we live in. But it isn't often systematized. Though having said that, I'm not at all surprised in hindsight, again, that it was physicists that were involved in the creation of the scaling laws research project in AI.
What are some examples of scaling laws? Like how might a scaling law sound when you state it to somebody who hasn't heard about scaling laws before?
So the easiest one to get a grip on is probably in image recognition. That if you have so much compute that you put into an image recognition model of a certain architecture, if you give it this particular size, then you could say that it will perform on this very large benchmark data set of images with this accuracy, say 85%. Say you have, I'm pulling numbers out of my hat again, but if you have a 10 million parameter model, that will give you, say, 85% accuracy. And if you have a 100 million parameter model, it'll give you, say, 93% accuracy. And every order of magnitude you add to it, it knocks another fraction between you and 100% of the accuracy off. And in language models, you might have a similar thing that, so I hesitate to use language models as an example here because the way in which you evaluate a language model is the entropy of its output. And it's just not something anyone has a handle on unless you actually study this stuff for a living. But in the same way, if you have a 10 million parameter language model, then it gives an entropy of output of this much. If you have 100 million, it's somewhat less and keeps going. And you could draw a line through these things and say, well, based on the 10 million, 100 million parameter models, here is how I think a billion parameter model will go. To connect this to my earlier thought patterns, I decided that maybe scaling the problem and scaling the AI simultaneously was an interesting research direction to take and would allow me to say something interesting about very big problems using very small amounts of compute. But having done that, the next question is, what kind of problem do you choose to work on? And my sense there was it would be a good choice to work on something fairly neglected. So image recognition models and language models are, people know these are cool and fun and that they do really interesting things. And so there is a lot of competition. And I have a general aversion to working on anything that lots of other people work on because it means it's going to be hard. There are lots of smart people in the world and just don't get in, pick your battles, pick something different. And games, meanwhile, have a lot of work on some specific games, Go and chess famously. But the nice thing about games is that unlike languages or images, it's widely regarded that there's an easier way to make that. There's a clear way to make them easier and harder. In that, if you play Go on a 3x3 board, it's a 3-year-old can figure it out. It doesn't take it. Go on a 3x3 board is basically like tic-tac-toe. Go on a 19x19 board is something that stumps grandmasters and is still a substantially open problem. So I've mixed together two motivations there. The first motivation is work on something that's less studied, games. And the second, work on something that's easy to scale up and down in a way that images and languages just aren't. There's no real sense of how you make language easier or harder. You can take good attacks on it. You can talk about formal languages or generative languages, but it's a fairly underdeveloped field. Games, meanwhile, games have got some serious work done on them by, again, DeepMind. There is an algorithm called AlphaZero, I think AlphaZero will turn out to be one of the more important algorithms of our time. So shall we take this detour? Or?
Yeah. I think this is good context because your paper is based on that class of algorithms. So.
Okay. So this, again, to try and connect this more clearly, having decided I was going to work on games because right level and neglectedness and easy to scale. The next question is, what kind of algorithms exist to play board games? Board games. And the clear winner here is an algorithm called AlphaZero out of DeepMind about 4 or 5 years back. And it was invented in parallel with a lesser known algorithm called Exit, I think it was. Something amplification. No, there were two papers that turned up at roughly a similar time, which explored this idea that if you have a neural network that plays a board game fairly well, how can you use that to generate a network which plays it better? How can you amplify the network? And the way they do this is by making lots of copies of the network in some sense and having them all play out slightly different versions of how this game could go. And then turning this into a target to train the original network against. So it's a bootstrapping setup in a sense. And you can certainly dive into the technical details if you want. There are a lot of very good explanations out there. I think Paul Cristiano's take on this as what he calls an iterated distillation and amplification setup is particularly insightful without getting into too much of the gory details. But yeah, this is an algorithm that I'm very much impressed by because of this bootstrapping property that can start off knowing very, very little and end up better than any human. Mm-hmm. And so this formed the foundation of my work because the nice thing about these kinds of algorithms is they require no input other than the rules of the game. They are independent in some sense, isolated. They require very little setup. I didn't need to go collect any extraneous data like other kinds of game playing algorithms would need.
And so what were the big, because as you say, you were able to tune the complexity of the problem, which is unusual. I think incidentally that feels related to the idea that the problems that humans find hard are not always the problems that machines find hard. And so to the degree that we can very straightforwardly say that like, oh yeah, a game of Go with these dimensions is clearly harder than a game of Go with fewer dimensions. it's almost like that's intuitive to us, partly because it's a problem class that we didn't evolve to find trivially easy, whereas language is this like really hard problem class, I think, objectively. But because evolution gradually structured the physical form of our brains to find specifically that kind of problem very tractable, it almost creates this illusion that that's actually like a much easier class of problem.
So this is okay. This is a bit of a detour, but I think it's an interesting detour in that there is an explicit hypothesis about this, that the kinds of problems that humans came to recently, things like chess, are surprisingly maybe the easiest ones to automate. And it's the really old capabilities like image recognition and language and motion are much harder because we have a lot of free circuitry given to us by our ancestors. A lot of mistakes were made in the discovery of these things, and it's resulted in very well-designed solutions. Whereas for chess, for example, it's been around for a few hundred years, and there's no selective pressure for one, and no real cultural pressure either to come up with very complex and subtle solutions. Having done a lot of work on games, I will still say that language is. There's a temptation in any kind of machine learning research to say that the problem you are in particularly working on is the important one, the key to intelligence. I will not claim that to board games for a second. I think board games are fascinating because they get at some of the real hard cores of intelligence without a lot of extraneous stuff on top. So, for example, some of the work out of OpenAI recently on, a better example, a lot of reinforcement learning research in this day and age is done in 3D environments, trying to get agents to navigate them, move things from one place to the other. And I can't help but think that what you are mostly doing in that case is trying to teach agents to see. Seeing is the hard part of that. And then there is some very simple behavior strapped on top. And I think board games are wonderful in that they get rid of all but the interesting behavior, the purest representation of the interesting behavior of like planning or deception or this kind of thing.
So it's like feature extraction is the hard piece, and then how you kind of jumble those features usually follows relatively simple laws.
I mean, chess was popular for so long. It's so popular because it's supposed to be some kind of reduction of the art of war. And war is this, huge, complex, terrible topic that you would have to build. You would have to have so many data ingestion systems to be able to actually train an AI that did something interesting with the concept of all of war. But training on chess, which is like what humans think of as like the distillation of war, we could do that in an afternoon. That you can get the data ingestion for that setup in an afternoon. It's like a very pure representation of what I find interesting about AI behavior.
Well, which is part of what I think is so exciting about what you're doing, because there's something about you picked a game called Hex, which maybe you can explain a little bit in a moment, like what the rules are, but it's a very simple game, and it really does allow you to quite directly map your sort of intuitions about like how hard is a certain scale of this game, and how surprised should I be that an AI can hit it with this much compute or whatever. Would you mind kind of, explaining a little bit of that game and the context?
Sure. So what we're going to discuss here is a mistake I made. In that we have established over the previous questions that I've decided to work on scaling AIs and board games simultaneously. I'm going to use AlphaZero to play these games. And then the choice is which particular board game to work on. And the obvious choices are chess and Go. These are like the well-known ones. And chess doesn't have an obvious way to make it larger or smaller, or harder or more easily. But there are like adaptations. You can do this, can be done. But the problem with chess and Go is that because they are games played by humans have added rules to them that make the games more interesting to play, but which make for a much more painful implementation. So chess, for example, has castling. So this is like an extra little twiddly bit that you have to add in your implementation. And chess is, in fact, there are so many other bits of chess. I think about around move repetition. That the kinds of people that implement chess engines for their hobby have built fairly serious bits of debugging infrastructure for figuring out whether your implementation of chess is actually right or not. And this just scared the hell out of me. That if I was going to give 6 months over to this project, then I didn't want to spend 3 months of it building a chess implementation. Yeah. This is not what I want to be doing. And Go, meanwhile, is nowhere near as bad as chess in terms of these like fiddly little rules, but it still has what's called the co-rule or the super co-rule, which says that no position can be repeated. And this is, if you want to write a slow implementation of Go, this is a trivial thing to do. If you want to write an implementation of Go that runs at like 100 million steps a second, then it's a lot more unpleasant to deal with. And so I turned to Hex. So Hex is a game that was invented in the 1940s and has developed somewhat of a cult following among mathematicians and logicians because of its utter purity as a game. It has a much simpler rule set. The easiest way to get your head around Hex is to just go look it up rather than have me explain it in words. But I will try and attempt anyway. In Hex, you have a hexagonal board. So each cell is hexagonal and it lies in a rhombus. So like a fallen over square. And there are 4 sides. There are 2 players, and each player gets the opposite sides of the board. And the objective of each player is to connect their sides of the board with tokens. And to do this, each player takes their turn and places 1 token on the board, either black or white. And the first player to connect their side of the board wins, and that's it. There are no other rules to the game. It's superbly simple, and this is what attracted me.
It's kind of like a Connect 4 in a different geometry, in a way.
Yeah. But this was a serious mistake on my behalf because it now means to explain my research, I now have to explain Hex. And that's good point. It's a real hang-up. It would have taken me a few more weeks to get Go working, and it would have been a substantially easier project to pitch to everyone ever if I'd made that choice. So yeah, grass is greener.
Though, I mean, I do think having looked at the rules of Hex in your paper, I mean, they're pretty straightforward. One quick GIF gets you there. And but yes, so what was really interesting here was as you scaled the complexity of the underlying problem, you saw, I mean, I don't know if it's correct to say a new kind of scaling law. Was this like a truly novel result? Had anybody else seen stuff like this before? I
have to eat some humility here in that we give the major explanation of why I undertook this work. But one of the hypotheses I had going in was whether the scaling with the problem size, with making the board bigger, would be nice and smooth, or whether it would be spiky. And spiky would be somewhat very interesting and extremely alarming, because it would say you can have your AIs trained on small problems and they'll behave in a predictable manner, and then you make the problem big enough and it suddenly stops being predictable. And this would be I'd be shouting this from the rooftops if it turned out to be the case.
And sorry, do you mind if I just ask a little bit more detail about when you say spikiness? Can you explain like what the x-axis is and what the y-axis is?
Absolutely. So, okay, well, I'll explain my results, then we'll go back and talk about the way they could have been. Yeah. So I took many different sized AIs and played them on many different sized boards. And I ranked the AIs in terms of their performance. And I found that as you make the amount of compute given to the AI, the size of the AI bigger, then its performance increases in a fairly steady manner. And in particular, if you double the amount of compute allocated to an AI, then it will beat the old version of itself about 2/3 of the time. So if you have your opponent with so much compute, if you have twice as much compute, you can win 2/3 of the time. That's like the nice, succinct Twitter tagline sale of this thing. And also, this is the same across board sizes. So you see the same thing happening on size 3, size 4, size 5, size 6, size 7, size 8, 9, which is where I ran out of compute. 9 was the biggest I looked at. And what's more, you can look at the performance of these AIs, and using the small AIs on small boards, you can predict the performance of large AIs and large AIs and large boards. Like, it is extremely predictable. You add 1 to the board size, and the amount of compute you require to hit the same performance goes up by about a factor of 10. So these are the two key things that double your compute, win 2/3 of the time, add 1 to the board size, 10 times as expensive. And it is, I could not believe when it came out to such round numbers. And I am, this is like some amount of salesmanship here in that the numbers are not quite that, but they're close enough that it's easier to remember than like 7 or 9.3 or whatever.
Well, you made a really interesting point in the paper itself. One of my first thoughts when I looked at it was, okay, are we learning here something about the algorithm, something about alpha 0, or are we learning something about the universe, something much more fundamental that you actually touch on in the paper, where you draw this analogy to how one might imagine, very speculatively, this process unfolding, where it comes. Well, actually, why don't I just ask you to explain that, because I thought that was so cool.
If it's the bit that I think you're talking about. So some backstory here. So I decided on this research project. I will come back to this later because it might be interesting to your viewers. I went out and got a small amount of funding from an independent research organization called Survival and Flourishing. to fund me over 6 months of worth of like fairly cheap runway. And then I had in late January some preliminary results, and I was wondering, are these interesting? And more importantly, are these just like batshit crazy? Because if your results are absolutely crazy, it means you need to go back and check you're working, check that you haven't introduced a bug somewhere. Because as an independent researcher, as the only person that looks at your code, it's very easy to come up with things that are just totally wrong and not even realize it until a lot of people have seen your work and you have to go back and talk to them all and say, I'm really sorry about that. It's not what I thought it was going to be. But when I put out these results, a guy called Paul Cristiano, who is extremely well regarded in the AI safety community, left a tiny little comment on my Google Doc saying, it's rather strange that when you double your compute, you get 2/3 of a win rate. That is roughly what would happen if you had just like two monkeys and they each had like a bag of possible strategies, proportional to the amount of compute you've given them, and they're just pulling strategies out of the hat, and the one that pulls out the better strategy wins. This is roughly what you get in that case. Or the monkeys have a clearer thing. Or if the monkeys have bags of numbers, and they pull numbers out the bag, you get as many numbers as you have compute, and the monkey with the highest number wins. And you can make a pitch, you can make an intuitive claim that maybe this is what our very, very complex, deep thinking AIs are doing. That for each ounce of compute that you give them, they find one new strategy and they play it against the other strategy the other guy is playing, and the one with the better strategy just wins. Now, I need to qualify this too, in that I studied one game with one algorithm on one set of hyperparameters, and I can only really say that it's serendipity that it came so close to double your compute to 2/3. It is entirely likely, it is easy to come up with thought experiments where this just isn't the case, that this behavior just can't hold. So the question is whether on other natural problems with other algorithms and other hyperparameters, you still see similar behavior, or just something totally different.
And it is interesting. I mean, if you did, it seems like it would say something about the process of problem solving, that there's a sense in which it all reduces to trial and error. Like there's a sense in which intelligence itself really is this relatively stupid process just directed in a fairly constructive way. Would you agree with that?
I would be extremely sympathetic to that. Again, all my reasoning here is unfortunately written through with deep uncertainty about the way the world is. But I have long been struck by how many processes in the world that we think are very smart do have the dynamics of random walks. So there is a fairly serious chunk of work over the past 20 years or so in economics on why, despite, if you like make a list of all the major discoveries over the last however many years, and you look at the size of the research community at the time these discoveries were made, you might expect that the research community today, being like 100 times the size as it was 100 years ago, might make 100 times as many discoveries. And it's just not the case. They still seem to turn up, major discoveries still seem to turn up at the same rate as they ever did. And the best one explanation for this is that we're a bunch of people wandering around in an ever-increasing search space, and we're just doing a random walk and pretending it's anything else. And we need to walk ever further for each new discovery, because this is like a broader frontier to cover. Of course, it being my work and me being keen on it turning out to be very, deep and meaningful, I'm very keen on the interpretation that this is what all problem solving is. Whether it's actually the case or not, give me 20 years and I'll be able to tell you.
Yeah, there we go. But now, if it is the case, just even more speculatively, you suggested that this is good news from the standpoint of AI safety, predictability, scaling, and so on. Could you connect those dots?
So after I proposed the project and after I'd started off this, I got to thinking, what kind of results would I actually happen to have? And I wasn't a good enough scientist to actually pre-register what I expected to happen, because there's just no need to do good science just right now in machine learning. It's too easy to get good results just falling out the sky. It's amazing. It's really a garden of Eden for research. But one thing that I was particularly interested in is whether the trends would be smooth as they turned out to be, or whether as you made the AIs particularly big or the problems particularly hard, you would see some kind of jump, some kind of shock, where the AI would come upon some realization, or the problem would support some kind of realization that just made it suddenly better. There'd be a strategy that a 10 million parameter AI could not discover, that a 10 million and one parameter AI could discover. And if this had turned out to be the case, this would be like alarm bells ringing. because it means that we could trip over any day now an AI and a problem set that was large enough to get some very surprising behavior out the other side. Because a lot of danger, not all danger, but like a good chunk of danger comes from things not behaving in the way that you thought they would.
Right.
The analogy I like to deploy here is that through the lives of some very poor nuclear scientists in the 1940s, we know how close to hold the plutonium spheres together. We know that if they come less than a screwdriver's width apart, then Harry Daghlian dies. And just don't do that again in future. Don't repeat that. And I kind of hope with the scaling laws research, we can get a similar kind of thing for AI as we do have for nuclear materials, or say spark gaps in electricity. We know how close together you can get to the higher voltage lines before something very bad happens. And there are lots of people in the AI safety community who will not consider this a good approach, because eventually someone somewhere will put the wires too close together or the plutonium rods too close together, and then extremely bad things might happen. But I think as a very prosaic, very mundane sort of safety, it is a thing worth exploring. And the fact that it didn't show up in this particular problem is like, it's a glimmer of hope that maybe these things are predictable and we can tell when bad things are going to happen, but without actually having to have the bad things happen.
Yeah, there's a ton of overlap with the broader question of safety, even the broader sort of course of human history. We talked earlier about the David Rudman sort of long timeline thing. One of the debates that he was talking about was whether there was this question about whether human progress has actually been continuous or discrete, whether the history of human economic achievement and advancement is to be told through these like stepwise moves or through relatively continuous improvements. And I was surprised by the strengths of the arguments that would say that things like the Industrial Revolution were not actually a step function, that, you know, even specific discoveries have some level of continuity to them. It'd be interesting to see if this generalizes beyond the sort of simple problem class of like hex.
Absolutely. And there is an issue here in that what you're trying to do is a proof of universality in the sense. So in mathematics, it's generally agreed upon that it is easier to prove that a thing exists than no thing exists. Proving that a thing doesn't exist is much harder than, like, you have to prove non-existence, much harder than proving existence where you just show the thing. So if we had one interesting problem where scaling the AI or the problem size suddenly went from predictable behavior to unpredictable behavior, or you were surprised by what happened as it got bigger, this would be, you only need it to happen at one time. But if we look at, again and again, if we look at natural problems, interesting problems, and we find no surprising behavior, this would be increasingly good evidence that we'll know we're in trouble before we're actually in trouble. Proof of non-existence. I have a sample size of 1. It's
right. Yeah.
Not so that you want to bet the farm on.
It's a start, yeah. But there is, I think, a sense in which there are two different kinds of continuity here. There's like whether this question of whether the universe is fundamentally continuous in terms of problem solving, or whether in practice we will interact with the universe in a way that makes it seem as if it's continuous. What I'm getting at here is, you know, OpenAI didn't make a model that was epsilon bigger than the model that was one step before. They made this giant jump to 175 billion parameters, 10xing what came before, which 10xed what came before. So we tend to take these very large leaps in model size, which through scaling work we seem to know, you know, correspond to fairly big leaps in performance. But there's a qualitative change that came with GPT-3, which I think was pretty surprising on the generality side. And I guess one thing I'm curious about is, like, while all these scaling curves that I've seen, they seem to do a great job of predicting the performance of these models on a specific task, the generality thing seems to me to be pretty unexplored at this point. Like, we don't have a metric for it, do we?
Some people are trying, they're doing this benchmark data sets, but yes, you're right that measuring generality is hard in a sense that when your model can do a thing, you stop thinking of that as general behavior.
Right.
And it's like, it's a God of the gaps phenomenon. That the generality is the model doing a surprisingly good job at things that you would not expect it to do. But the moment you expect it to do well on a thing, it doesn't count anymore. But to get on to focus on, I think the question of whether to think about things as step functions or as continuous phenomena is a very deep and difficult one. I think a lot of it hinges on your choice of scale. So, for example, when I was born, that was a very important event for me. But you zoom out and you look at the world as a whole, a lot of people were born that day. And it's much easier to think about it as a continuous phenomenon of this is how many people are born each day, rather than this how many of me were born that day. And I think Yeah, it's choosing the right scale to think about the universe is, or those just, how do you even start on that? I mean, you're the physicist, and I know this is, your back garden of choosing the scale at which Keplerian motion works out versus zoom a bit, and suddenly Mercury's processing in the wrong way.
I mean, I think what you usually do in those contexts is you pick the thing, you pick the scale that's most relevant to the phenomenon you're interested in. And in this case, from an AI safety standpoint, we talk about AIs that have the ability to make AIs and improve on AI research, that sort of thing. That sort of seems to be like that's a very ill-defined term, right? I mean, we're glossing over a whole bunch of detail, which arguably is precisely the phenomenon you're gesturing at with this. But giving myself that out, I mean, I might imagine leaps of that size, where the kinds of leaps that that we find. I have no idea how you'd quantify this. I'm talking myself in circles, I guess. I think you're completely right is the short answer.
Okay, well, let's, okay, so yes, I think you're right that the choice of scale hinges on the phenomena you want to investigate. And so we'll take the future of AI as an example, where you can make one thesis that the key point is when an AI can write its own software. But it is very plausible that AI will be helping to write its own software for a long time before it actually does. It is almost certain that AI is already used by NVIDIA to optimize the layout of its chips. It will almost certainly be used as code complete for programmers long before it's actually writing full software. And so this is going to be a thing that's won by inches in a sense. And it'll be a long time. There'll be no specified point at which we go, that was the moment that an AI wrote itself. Because certain people, they will, even when the first AI writes its own software stack end to end, there'll be someone that goes, well, it didn't write the chips, did it? It didn't run the factory. Go to the gaps again.
Well, does that imply its own challenge for safety? I mean, humans are notoriously bad when it comes to incremental, especially exponential incremental phenomena. I mean, you only have to look at COVID to say, well, it's only one case in the city, and well, it's only a small cluster. Well, it's only 10% of the population. We kind of gradually have this goalpost moving that you've alluded to.
It depends whose perspective. Okay, I think this plays into a fairly difficult question in ethics of whether what is good from the perspective of you right now, or what is good of you from the perspective of the future you. In the sense that we consider our society today to be much more ethical and humane than historic societies. But if you dug up some pilgrims from the 1500s and dropped them into today's society, they'd be horrified. They'd be utterly, and in the same way, we might now look at things like AI-induced unemployment and go, that's terrible. Work is required for human dignity. And in 50 years' time, people could look at us like complete morons. Why would you ever think that work is key to human dignity? What's wrong with you? And I am frankly entirely stuck on whether I should reason about what is a good world from the perspective of what I today would consider to be a good world, or what I in the future would consider to be the future good world. And slightly more frustratingly, upsettingly, what the survivors of, what in 100 years, the people that are still around, the entities that are still around, will have been selected in a fairly serious way based on who did well in the world that has been. And they will very likely think that what happened was a good thing because it allowed them to turn out to be who they were. Is that a thing I want to optimize for? And so how do I trade that off against projecting my own ethics into the future? I have no answers here whatsoever, but I think Will MacAskill's doing some fairly serious work on this, and I assume other philosophers are, but his is the big name that I remember, much to the apology of all the other philosophers who have looked into this.
No, I think it's a great point, and it shows you how inescapable the tie-ins to all kinds of different philosophical and moral questions are. I mean, this really is an intrinsically multidisciplinary topic. And to your point about the future versions of ourselves having to be respected to some degree to make their own decisions, it's sort of the flip side of that to me is you look at something like Twitter, which is designed to be incrementally seductive. And I right now recognize myself as having an addiction to different forms of social media that coax me into interacting with them through this sort of like frog in hot water gradual effect. You could imagine something similar happening with AI, where we get this economic benefit and it feels good until it all of a sudden doesn't.
Yeah, I think you can only look for historic parallels here and say that, as with all things, they worked out very well for some people, very badly for other people. What do we use that to say about an average? I it's choosing your reference class is the key thing here, and I'm not the faintest how to do it properly. I'm still stuck between choosing humans, mundane technology, or machine learning that we have is like the key way to think about the future, and also about whether the better analogy is like genetic engineering, where we clamped down pretty hard on it in the 1990s, and a lot of people consider it a very good thing, and some people who are worried about food. Oh, you can make the pitch, for example, that the lockdown on genetic engineering in the 1990s was very bad for people who wanted cheap food. Right. It was very good for some environmental movements, very bad for the others. You can make the pitch that the lockdown on nuclear energy was very good from the perspective of preventing proliferation and radiation hazards, but very bad from the perspective of we've burnt a lot more coal than we needed to. And yeah, I am struck. It's a cliche and naive thing to say, but I'm struck by the subjectiveness of these decisions. And I have really no other way to resolve them than to try and think very hard, talk to a lot of people, and hopefully we figure this out all together.
That's a really important kind of dose of humility to infuse into all this as well. And it's something as well, it seems like there's also the countervailing risk that I see in myself, especially with politics, where I'm sort of like proudly confused in politics. And I think, and I'm embarrassed of the proud part, if that makes sense, as paradoxical as that seems. Like, I recognize that things are very confusing and complex, and that it's very easy to get sucked down sort of partisan rabbit holes and get sort of lose your identity in this process. And yet at the same time, I also know that these areas are unquestionably important. And so neutrality for pure neutrality's sake is its own sort of failure mode. And yet I can't disentangle those things. This seems like one instance of that, right? Where like the far future is super important. And yet what should we do? Like, you can get lost in epistemology and moral and
this is
sort of...
Yeah, it's there's a phrase for this that ends with paralysis, but I can't remember what the first noun is.
Oh, analysis paralysis?
And possibly, yes. Tool paralysis, something like that. No, tool paralysis is a different thing, but the same kind of concept of just future shock, present shock, that you look at the world around you and it's great and enormous complexity and go, how the heck do I even, where do I start?
Yeah.
And all I can offer is that all your ancestors likely did this. And then you are at the end of a long line of people who are terrified by the complexity of the world around them, and yet managed to accomplish something. There is again, some kind of hedonic treadmill in a sense of you start off terrified at this thing, but you do get on with your life. And the people there at the end are the people who just got on with things and tried to find some small piece they could work on and delegated the rest to someone else. And you're right that I will equally admit to being confused about an awful lot of things, politics included. I can't say I think proud. I think, yeah, I would say that proud confusedness is very close to humility, and that is a thing that I'm entirely on board with. But no, you've caught me out here. Like, all I've got here is like mumbling about various.
But I think that sort of summarizes what confusion is, right? I mean, at the end of the day,
yes.
To the extent that that's the point here. But I do think there's something to this idea that that blind panic, especially in the face of change and change induced by AI and AI risk, which is something that I fell into. It's something that I definitely saw on Twitter an awful lot around this time from the AI safety, AI risk world. I think there's a sense in which it is self-defeating and counterproductive at a certain point, where people resign themselves to like, oh, well, there's going to be an apocalypse and whatever. First off, I'm not sure that maps onto the objective probabilities we're dealing with here, but also it kind of strips you of your agency when you take that sort of fatalistic mindset as well.
There's a phrase from a fantasy book, a fantasy series that I'm keen on, which is the important thing is to get into the future. Don't get hung up on whether what you believe right now is the true thing or the best thing. If that's going to lead to paralysis, then put that aside for a moment and just work on getting to the future. And certainly I have friends who have found themselves paralyzed by self-doubt. They will not allow them to do themselves. They feel that they are not particularly good at a thing, and their doubt about their ability to do a thing stops them from getting any better. That's the key characterization of this, and I think something that everyone can sympathize with. And it turns out the way you deal with that is that it's harsh advice, but you deal with it. If it helps to find a community of people that sympathize, if it helps to read Marcus Aurelius or CBT or whatever, they go ahead. But the key thing is that you get yourself into the future. You do something you will end up being the person that got past it. But we're getting into pop psychology here. I don't think I'm offering anything new or different other than it applies to me too.
I think pop psychology and the parts of it that people in AI safety have distilled as being particularly relevant is sort of an interesting selection study in and of itself. But I think on that highly pragmatic note, I really appreciate it. I think we've run over our officially allotted time here, but I just enjoyed the conversation so much.
Absolutely, this has been wonderful.
Yeah, thanks so much for sharing your insights, Andy. And oh, sorry, go ahead.
I need to make one last call out, which is that if you are interested in doing this kind of work yourself, if you're listening and you think, maybe I can do independent research, I would strongly suggest you look into it. This is another part of just, if you see a problem in the world, put it on your own shoulders and walk. And there are organizations which will lay out cash to people that they think have promising research problems. And the ones to look into are what are called the Long-Term Future Fund, which is run by an effective altruist charity. And more recently, there is one called Survival and Flourishing, which is the one that I got my small amount of cash. And these are not rich organizations. It's not a thing that you can make your living off permanently. But if you're looking for a way to get out of whatever income trap you're in at the moment, then I think it's an excellent place to start.
That's a great point. I'm really glad you brought that up, actually. So I will make sure we include links to those, and there might be a couple more funds. I'm trying to think. I think
absolutely. If you know more, then please add to the list. Yeah.
Okay, great. Yeah, but I think those are great. And Survival and Flourishing in particular, I think that's the one that funded your specific research, right?
Yes, it did.
Hex. Okay, great. So yeah, we'll link to all those, and thanks for sharing your story and your suggestions as well at the end there, Andy. I really appreciate it.
Yeah. Thanks for listening to me for an hour and a half. Yeah, it's been great.